All right, so welcome to lecture 15. So today we'll be starting the uniformly most powerful tests. So this is a follow-up of the previous section that we discussed. In the previous section, if we remember, we discussed the most powerful test given the same critical region, how to choose the most powerful test. Okay. Um, then we had the test, the Neyman-Pearson test that we discussed. Now today we'll be sort of building on that. So we'll be considering a null hypothesis, which is a simple hypothesis, against an alternative hypothesis, which is a composite hypothesis. Okay. So let's get started. Okay. So this is called the uniformly most powerful tests. And what we have is we'll be testing to test a simple hypothesis H0 against an alternative composite hypothesis. Okay, so the alternative hypothesis here is composite. H1. Okay, so that's the difference between this section and the previous section. In the previous section, we considered we are trying to develop a powerful test, the most powerful test, or a most powerful test, which is comparing a simple hypothesis against another simple hypothesis last time. Okay, let's start with an example. So here is an example. And this goes like this. So let's say consider the PDF, which is given by f of x theta, which is an exponential distribution, 1 over theta, e to the minus x over theta, and 0 elsewhere. So it's exponential, right? We have seen before in the last class. So we ended this. Let me show you something from the last class. So we had this function. Now we tested the simple hypothesis theta prime equals to 2 against theta double prime equals to 4, another simple hypothesis. And we developed a test. And if you recall, the test is, so the region is x1 plus x2 is bigger than c. And this is essentially, so we can set this c to be a chi-squared with the degrees of freedom 4. And the level of significance is 1 minus alpha. So level of significance is alpha, but this chi-square value is it's 4 comma 1 minus alpha. Okay. So that is what we developed. Now, at the very end of last class, we have also seen a problem when we said that generalize this result for theta double prime is bigger than 2. And we have seen that this is also true. Okay. So what we can conclude is last class, we have seen that to test the null hypothesis H0, which is theta equals to 2, against the H1, which is theta bigger than 2, from a random sample of size 2. So random sample is x1 and x2. And the critical region the critical region should be x1 plus x2. As we have seen, it's bigger than equal to chi-squared 4 1 minus alpha. Okay, so now let's see if we can set up some alpha value. So suppose this alpha is a 0.05. Okay, so then let me share my screen. So basically we have to compute. So x1 plus x2 is bigger than chi-squared 4 comma 0.95, right? And let me share my screen so that you can see one of those tables. Again, it's I just use a free calculator. So I have degrees of freedom 4, and then the level of significance is 0.05. So if you can compute this, you get 9.445 for 9.48. So it's about, so this value is 9.45. So that means this is the critical region. So if x1 plus x2 happens to be bigger than 9.45, then we reject the null hypothesis, right? So so this is how we can compute the critical region. So the critical region is C, which is x1 plus x1 comma x2, such that it's about 9.45 less than x1 plus x2 less than infinity. Okay, so that is something we have seen before. So this is based on the last two examples of the last class. So this is for the best test and is the best critical region. Okay, now one more thing, even in this case, one thing is very clear from here that there is a difference between this problem and what we did in the previous section. So in the last section, we are considering H0 against a simple H1. So now we have H0 against a composite H1. Okay, so that's the difference. But we have seen, I mean, today we are just building up with last two examples of the last class. And we are seeing that even in this case, I can safely use this as a critical region. Okay, and that will be, this will be a powerful test, the most powerful test. Okay. Now, before we proceed further, let me just also show you one aside here. So this is not directly related, but we can also compute the, we can also compute the power of the test in this case. Okay. Now let's see for a power function. So theta gamma. So we write gamma of theta. So this is the power function. Do you recall what it is? So it's basically probability of your random variable. So here in this case, x1 plus x2, x1 comma x2, this two random variable. So this is in the domain of C. Okay. With respect to certain alternative hypothesis. Okay. I didn't specify theta here. So with respect to certain theta. With respect to theta. For instance, in the case of the alternative hypothesis, theta is bigger than 2. Right? So let's compute this. So I can write this as, remember what is C? So C is really the region where x1 comma x2 such that 9.45 is less than x1 plus x2 less than infinity. So that is my C, right? Now I can write this as 1 minus probability of x1 plus x2 in C complement. Why I did that? Because it's easier to deal with this one. So this is going to be, so it's basically x1 plus x2 is less than 9.5. So we are integrating. So we have x1 plus x2 equals to 9.5. So the straight line which gives you x1 plus x2 equals 9.5 is something like this one. So this is my x1, and these are both exponential random variables, so they are positive. So this is the straight line x1 plus x2 is equal to 9.45. So if we want something which is less than, so I can just pick up with my favorite point anywhere I like. So say 10 here. So now if I compute, so basically, so there is a point 10 comma 0 here, and for this x1 plus x2 is 10, which is bigger than this one. So this is the region I'm talking, right? So that is the region of C. So what is C complement? C complement is basically right here. Okay, so that means I have to integrate here. So it's basically I have to go for the x-axis. So it's 0 to 9.45 minus x2, and then I have to put this strip up and down between 0 and 9.45. So this point is 9.45, and this point is 9.450, right? Yeah, it's a very simple double integration. So it's basically 1 minus integration of, let's do it here. So it's 1 minus integration of, if I take the x2 variable, so it's from 0 to 9.45. And if I take x1 variable, which is from 0 to 9.45 minus x2, and then 1 over theta squared. I'm just integrating the joint PDF because they're independent. So it's 1 over theta squared e to the minus x1 plus x2 over theta dx1 dx2. Right? I'll leave it as an exercise. It's a very easy one to compute. And if you compute this, you'll get it as theta plus 9.45 over theta e to the minus 9.45 over theta. For so here I'm assuming that theta is bigger than equal to 2. By the way, that, we are assuming this because that is our domain for theta. So that is where we started off with. I probably didn't write it here. So remember that if we have the null hypothesis this one and alternative hypothesis this one, so what is omega? What are the possible values of theta? So that is, this is theta such that theta is bigger than equal to 2. So these are the all possible values of omega, right? So all possible values of theta are from this. And hence I wrote theta is bigger than 2 because I mean my theta, whatever it is, it got to be in the omega, right? And now we can compute this gamma of theta. So for instance, you can put gamma of 2, it's approximately 0.05. Gamma of 4, you compute this, it's approximately 0.31. Gamma of 95, you can compute this approximately 0.74 and so on. So these are all the values. So power of the test corresponding to various values. Okay. So therefore, also a note. C, which is constructed out of this one, x1, x2, 9.45 less than x1 plus x2 less than infinity, is a best critical region of size 0.05 for testing h0 theta equals to 2 against h1 theta bigger than 2. Okay, so why is this the best? So as we mentioned before, so also as seen so we have seen earlier. By the Neyman Pearson test that we showed that no matter what the value of theta is, as long as it's more than 2, so this is the best region. Okay, now this gives us a way to construct a best critical region when we are testing a composite hypothesis. Okay, so for null hypothesis, it's basically a simple hypothesis, h theta equals to 2, and against the alternative hypothesis is composite 1. So basically we can find a uniform way of testing this kind of hypothesis and finding a best critical region. Okay. We are now ready to define based on this one. Remember, this was called the most powerful test in this case because we have the best critical region. So now therefore we can define something called the uniformly most powerful test definition. So let's define this. The critical region C is a uniformly most powerful, or it's called UMP critical region of size alpha for testing the simple hypothesis H0 against an alternative composite hypothesis H1 if the set C is a best critical region of size alpha for testing H0 against each simple hypothesis in H1. Okay, so basically what we are saying is think about the last example. So it's a best, so it's called the uniformly most powerful critical region provided, think about the last example, the simple hypothesis like theta equals to 0 is against an alternative composite hypothesis. For example, here theta is bigger than 2. It's called the uniformly most powerful critical region if the set C is the best critical region of size alpha for testing H0 against each simple hypothesis in H1. For example, in the last example case, so take any value of theta so that theta is more than 2. So theta equals to say 3, theta equals to 4, theta equals to 2.5. Whatever you take, this is your critical region, right, for this test. So that is why it's called the uniformly based critical region. So that's why I did this example first, and then this is a follow-up. So the last example, what we found is the uniformly most powerful critical region, this one. Okay, and also a test defined by the by this critical region C is called uniformly most powerful test, UMP test. So we define two things. So we have defined the most powerful critical region, and based on that, the most powerful test. We have done it before, and now we are defining the uniformly most powerful critical region, and based on that, we are defining the uniformly most powerful test with the significance level alpha. Alpha for testing simple hypothesis H0 against the alternative composite hypothesis H1. Okay. So that's the definition of the uniformly most powerful test and corresponding to the uniformly most powerful critical region. Okay. Now let's do an example to understand this. So we have already done an example. Okay. So example, for the first example, in the case of last example, the C, which is equal to x1, x2, given by 9.45 less than x1 plus x2, is uniformly most powerful critical region of size alpha equals to 0.05 for testing theta H0, which is theta equals to 2, against H1, which is theta bigger than 2. So we just wrote this term, uniformly most powerful critical region. And therefore, this is the uniformly most powerful test. Okay. All right, let's do one more example. So here's the second example. Let x1, x2, xn denote a random sample from the distribution, the normal, 0, and theta. So note that my variance is square root of theta here. Sorry, variance is theta, so standard deviation is square root of theta. All right. We'll be trying to want to find an uniformly most powerful test with significance level alpha for testing the following hypothesis. So H0 is theta equals to theta prime, where this is a fixed positive number. So we are trying to estimate this one against H1, which is theta bigger than theta prime. Okay, so the set which you are concerned with, so omega, so the set of all possible values of theta is really theta can be either theta prime or more than theta prime, so theta bigger than theta prime. So theta such that you can write the set this way, theta bigger than theta prime. Okay, so what is this one? So this is the set of all possible values of theta. So it can be either theta prime or it can be more than theta prime. So it's bigger than equal to theta prime. So this is a set of all possible values of theta. Okay. All right, so let's compute this. So the way to compute this is, well, first of all, what is the log likelihood function? So to find this, first of all, we have to find the log likelihood function. So what is L of theta? So it's the log likelihood function for the normal distributions where the mean is 0 and variance is theta. So it's 1 over square root of theta, square root of 2 pi. So it's square root of 2 pi theta. And I'm writing for 1 first. So e to the minus xi, x1, xi squared over 2 theta. And I have to take the product of all possible. So I from 1 to n. So what I get is n of those. So I can write this as 1 over 2 pi theta, and then there's a square root sign, so I can write n over 2. And then this one is becoming the summation, so it's becoming e to the minus 1 over 2 theta summation I from 1 to n xi squared. Okay, so that's the log likelihood function. Okay, now let's consider a number theta double prime bigger than theta prime. Okay, why theta prime? Because remember that my alternative hypothesis is all the values of theta, so that it's bigger than theta double prime. So I'm choosing a particular number. So this is a particular number that is bigger than theta prime. Okay. Also let k bigger than 0. So k denotes a positive number. So the idea is I'll be using the Neyman-Pearson test. Okay. So with this like with these assumptions, this and this. So let C be the set of points. By that I mean x1, x2, xn, such that L of theta prime over L of theta double prime is less than or equal to k. This is the setup for the Neyman-Pearson test, right? Let's simplify this. So I have all these values, so I know how to compute this. So basically, when I have a L of theta prime, I'll replace theta by theta prime. When it's a L of theta double prime, I'll replace theta by theta double prime. So if I did that, and if I simplify, so that means I will have theta double prime over theta prime to the n over 2, because 2 pi gets cancelled. And then I have e to the power of minus theta double prime. Please check it yourself. So this is a very simple calculation, theta prime, theta double prime, and then summation I from 1 to n xi squared, that is less than k. So x1, x2. So what are the set of points? So here you can see it more explicitly. So this set of points are satisfying this relation. Equivalently, so this really means, by the way, this constant k, it can be a function of theta prime. It can be a function of theta double prime, right? So I mean, all I need, I need to find a constant. So I'm trying to find a region, a set of points, so that this is true. Okay. Now, this points for a given value of for a given value of theta double like double prime, it depends on that. So just I mean, as long as you're finding a constant which is bigger than 0, so you're fine. So I mean, I can just take this constant dependent on anything I want. For example, I can take say theta double prime. It's a function of theta double prime. So let's write here theta double prime. Okay. As long as it's a positive number. Okay. All right. So after this one, so let's see. So if you simplify this, if you take the logarithm of this quantity, so what we have is log of so n over 2 log of theta double prime over theta prime minus theta double prime minus theta prime over 2 theta double prime summation I from 1 to n xi squared is less than log of k theta double prime, right? And I'll leave some simplification up to you. So if you simplify this, you're going to get I from 1 to n xi squared. So I'm simplifying for this one. So this is going to be equal to bigger than equal to theta double prime, theta double prime minus theta prime. And then you have n over 2 log this quotient minus log of k theta double prime. So that's what you have. Now look at this quantity. So this quantity, since theta double prime is bigger than equal to, since theta double prime is bigger than theta prime, so this is bigger than 0, right? So therefore, this quantity is positive. So I can write this is bigger than equal to, it's just the next one, log k theta, as I already know that this quantity is bigger than that. This is the notation for since, okay? All right, now let's choose. So choose. So that's the fun part. So k theta double prime to be some e to the minus, I'll choose the opposite of this one with the flipped side. So theta double prime minus theta prime to theta double prime times c for c bigger than 0. Okay, so then this summation I from 1 to n xi squared, I'm just copying this one, is bigger than equal to, and then it becomes theta double prime minus theta prime to theta double prime times c, right? Which is really c, which is independent of theta double prime. Okay. So that's the motivation, or that's the idea behind this calculation. So we are trying to get a constant that is independent of c, and hence what we can say is therefore remember that when we choose this k theta double prime bigger than 0, and that is also true here, right? So it's bigger than 0. So as long as this is satisfied, my Neyman Pearson test is satisfied. So I'm getting a base critical region. Okay, for a base critical region for theta double prime. But in order to make it uniform, I have to get something which is uniform, right? So so this critical region is true for every possible theta double prime because my constant is independent of theta double prime. So therefore, the set C, which is given by say x1, x2, xn, such that so this quantity is bigger than C, such that I from 1 to n xi squared is bigger than C, is the best critical region for testing H0, the simple hypothesis, against against the simple hypothesis theta equals to theta double prime. But note that I wrote here simple hypothesis theta is equals to theta double prime. But it's the constant that we got. For the critical region, it's really it does not matter as long as my theta prime is bigger than this theta double prime. So we are fine, right? So that is what I'll be writing next. So that means that we don't really have to take a simple hypothesis. This argument holds for every value of theta as long as it's bigger than theta prime. Okay, so C, which we wrote before, x1, x2, xn, such that summation I from 1 to n xi squared bigger than C is uniformly most powerful critical region. Critical region. Okay, now suppose we want to make it a size alpha. Okay, so if we want the size of this critical region, want the size of this uniformly most powerful critical region to be equals to alpha. So then what do you have to do? So we have to consider, so alpha would be the size of that. So that means with respect to the null hypothesis, we must have xi squared, I from 1 to n, bigger than C. So that got to be alpha, right? Now note that each of these xi's, they follow a normal distribution. Under the null hypothesis, they follow a normal distribution with mean 0 and variance zeta prime, right? For I equals to 1 to n under H0. Okay. So if this is normal, I mean, you know that it's a square of the normal. So if I divide it by the variance, so that means what I can write this is I can modify this a little bit. I can divide with the variance I from 1 to n xi over theta squared would be less than, so sorry, square root of theta squared. So it's C over theta, right? So I'm dividing both sides by theta, and I'm just putting this theta inside. Now this is, we know that xi over square root of theta in this case, sorry, theta prime. Let's use prime because that is the variance. Theta prime follows normal with 0. From here we get that. Okay. So what about the square of this one? So it's a standard normal. So square of this one follows a chi-square distribution, right? So it's a chi-square distribution with 1 degrees of freedom. Therefore, this one follows the chi-square distribution, I from 1 to n xi over square root of theta prime squared. It follows chi squared with n degrees of freedom. Okay. So what we are really trying to see is we are trying to see that this is a chi-square distribution with n degrees of freedom. So all we can try to check is we can have a level of significance of alpha. So this quantity can be written as so we can choose, if we want this to be alpha, we can choose the c over theta prime to be equal to chi squared n 1 minus alpha. All right, so we can like this quantity is that one. So now we have even a control of the size of this uniformly most powerful region. So hence uh, alpha can be thought of theta prime I from 1 to n xi over square root of theta prime squared is bigger than chi squared n 1 minus alpha. Okay. So this is so the size alpha of that uniformly most powerful test. Okay. Let's take a quick example. Let's take, say, n equals to 15, alpha equals to 0.05, and theta prime equals to 3. So we are trying to test, so h0 is theta equals to 3, and h1 is theta is bigger than 3. So for the uniformly most powerful test, therefore we must have, so we observe that chi squared, in this case, n equals to 15. So 15 comma 1 minus 0.05. So this quantity is 24.996. Okay. So hence, what should be that C? So this is the equation to keep in mind. So therefore, C over theta prime, which is 3, equals to 24.996, right? Because of this equation by star. Okay. And therefore, what is C? C is 74.988. So this is the value of C which should be used for the uniformly most powerful test. Okay. Once again, let's go back and forth. So here, why is a C necessary? Because I'm trying to construct this set. And I'm saying that this is the best critical region for testing. Okay. So for doing that, I need the value of C. So what we found is if n equals to 15 and theta prime equals to 3 that we are testing, then the C got to be 74.988. Okay. So that's a very quick example of showing how it works. Okay. All right. So let's do another example. So this is problem number 8.2.7 in the example. So example. So this is exercise 8.2.7. Okay. It goes like this. Let x1, x2, x25 denote a random sample of size 25 from a normal distribution n of theta comma 100. Find a uniformly most powerful critical region of size alpha equals to 0.10 for testing theta equals to 75, which is the H0, against H1, which is theta bigger than 75. See that here is a composite alternative hypothesis. So that's why we are talking about the uniformly most powerful critical region. Okay. So here is a solution. So let's compute, say, L of 75 over L of the null hypothesis, which is over the L of theta. Okay. For theta prime bigger than 75. So I'm choosing a particular value of theta so that it's bigger than 75. And so I'm calling that particular value to be the theta prime. So remember what we're trying to do. So here we write the null hypothesis. So here in this case, it's basically 75. That's theta equals 75. Let me just write another way so that it looks a little better. So it's L of theta equals to 75 over L of theta prime, which is bigger than 75. So that's what we are trying to test. Okay. Let's compute this. So if you compute this, so in this case, there are random sample from the normal distribution. It's easy to do it. So it's going to be e to the power. So all the they have the same variance 100. So the variance part gets cancelled. So all it takes is basically e to the minus 1/2 summation I from 1 to n, I from 1 to 25. For this one, it's xi minus 75 over 10 squared, right? So 10 because the standard deviation is 10, and divided by, so this is just e to the minus 1/2 I from 1 to 25 xi minus, so I'm trying to estimate the mean, which is theta prime over 10 squared. Okay. So that's the quantity. So basically we have here 10 squared in the denominator, which comes with 2, which makes it 200. So it becomes e to the power of, and here the same thing. So if I simplify this, it's going to be minus, I'll leave it up to you. So it's minus theta prime minus 75. And then summation I from 1 to 25 2xi minus 75 minus theta prime over 200. Okay, it's up to the simplification. You can simplify this. What we want is, we want this to be less than some k of theta prime, where k of theta prime is bigger than 0. Right. Let's simplify this. So we have minus theta prime minus 75. I take the logarithm. I from 1 to 25 to xi minus 75 minus theta prime over 200 is less than log of k theta prime. Okay. If you simplify this whole thing, you should be getting, I'll skip the calculation, you should be getting this 2x, so summation xi, I from 1 to n, is bigger than 100 log of k theta prime over theta prime minus 75 plus n of 75 plus theta prime over 2. Okay. So that is the quantity we are getting. Please note that this k of theta prime is bigger than 0, but it may be less than 1. So consequently, this number can be positive or negative, right? But then we can use a common trick. So I can take this log of e of theta, like we can take k of theta prime to be, say, e to the this quantity. Okay. So choose k of theta prime to be, say, e to the theta prime minus 75. So it's always bigger than 0, right? And hence, what we have from the last statement, summation I from 1 to n, I to 25 xi, is bigger than equal to 100, and then it's theta prime minus 75 over theta prime minus 75 plus n 75 plus theta prime over 2. So at least one of the theta primes are gone. Okay. Now note that this whatever this theta prime is, that's a positive number, right? So because we are trying to estimate this, from here. So theta prime is bigger than 75, right? So its least value is 75. So that means I can write this is bigger than, if I just replace this theta prime by 75, so it's plus n 75 plus 75 over 2, since this is the notation for since theta prime is bigger than 75, right? So here is theta prime, here is 75. I'm just making this. So here, therefore, I have summation I from 1 to 25 xi is bigger than, so this is 75 plus 75 is 150 over 2, which is again 75. So it's 100 plus 75n. Okay. By the way, I am always using n equals to 25. So let me just write n equals to 25 here. So because, I mean, this n is really 25. Okay. So this is 25 because I used n here. Later on, I changed this n to 25. Okay. So this n is 25. So this is 25. So this is 75 times 25. I don't worry about this number. For my purpose, it's just a constant c. Okay. So hence, we find that for every theta prime bigger than 75, we have this I from 1 to 25 for this particular sample. Xi is bigger than C. Okay. Now we are trying to do. We are trying to find a uniform most powerful critical region of size this. So it's usually this is a sum of random variables. So we don't have much control over this one. So the most obvious thing we can do, you can compute the mean from this. So that means 25. If I divide this, xi is bigger than c over 25. That's always another constant. Okay, so let's call c prime. So c prime is c over 25. Okay, so that means my x bar is bigger than c prime. Okay, and this is true for every theta prime is bigger than 75. Hence, this c, which is computed as all the x1s, x1, x2, x25, so that x bar is bigger than c prime, is the uniformly most powerful critical region. But we know that that's this all this xi's, but under the null hypothesis, under H1, H0, so x2, x25, each of these random variables, they follow a normal distribution with mean mean 75. That is your theta. That's what we're checking. And the variance 100, right? Okay. So that means x bar satisfies a normal distribution with the same mean. So and then we have to write the variance over n. So it's 100 over 25. So that is n of 75, 4. Okay. Therefore, so let's look at this critical region right here. So x bar, it's more than some c prime, really means x bar minus 75 over 2 is more than c prime minus 75 over 2. And this is nothing but the z, right? So that means z is bigger than c prime minus 75 over 2. So now let me just remind you one small fact from what you must have studied in the previous courses. So this is, I think all of you know this, but still I think it's my responsibility to let you know. So if I write ZP, so I really mean this area is P. So this area is P. Okay. So for example, if I want to compute something to the right, so suppose I'm having this region and this is alpha. So that means the region to the left is 1 minus alpha. So this one is z of 1 minus alpha. Okay. So if you specify the right one, if you specify the right one, then the left one is it will be z of 1 minus alpha, right? So now based on this this observation, so what we have, we are trying to find z is bigger than 1 minus c prime minus 75 over 2. So if we take alpha to be 0.10, so then what we really want is 0.10 to be probability of z bigger than c prime minus 75 over 2, right? And therefore I have c prime minus 75 over 2 from this picture. So look at this. So my this quantity is like this alpha, right? So I have to write this z of 1 minus 0.1. So this is not like this one, right? So it's z of 1 minus alpha. So therefore, if I compute this, what I end up with is c prime minus 75 over 2 is z of 0.9, which is, you can find from the table, it's 1.28. And that means if I can solve for c prime, it becomes about 77.56. Okay. That's pretty much it. And hence, H0 is rejected. Remember the region. So H0 is rejected for this one. So for x bar bigger than 77.56. So that is our uniformly most powerful test. And so the question is to find the uniformly most powerful critical region. So this is the uniformly most powerful critical region. That is in terms of x bar. So there are two ways of answering the question. So the first way is just by observing this one. So this is B1, more elaborated later. And then we studied this region and we are trying to understand this, I mean, this quantity in a little bit more details. And we found that if we specify a confidence interval, say alpha equals to, so if we are specifying the level of significance, alpha equals to 0.10, then maybe this one. So this one is, let's call this B2. So this has a definite level of significance with it. Okay, so these are two ways of understanding the uniformly most powerful test in this case. Okay. All right, so after this one, so let's consider maybe one last problem, which is so this is exercise 8.2.12. It goes like this. So let X have the PDF f of x theta, which is theta to the x 1 minus theta to the 1 minus x for x equals to 0 and 1. Okay, and it's 0 everywhere else. We test h0 theta equals to 1/2 against h1, which is theta less than 1/2, by taking random samples x1, x2, x5 of size n equals to 5, and rejecting h0 if y equals to xi, I from 1 to n is observed to be less than or equal to a constant c. Okay, so that's the scheme of the test. Number A, part A is show that this is a uniformly most powerful test. Okay. So now, in order to show that this is a uniformly most powerful test, so we have done a very similar problems before. So let's very quickly do it. So solution for the first one. So what do we have to check? So we have to check that. So basically, L of theta equals to 1/2. We are testing against the alternative hypothesis. So it's over. Let theta prime is a number which is bigger than, sorry, less than 1/2, right? So over theta prime. Let's compute this. So what is this one? So this quantity is basically 1/2 to the summation of xi. So there is a random sample of size 5. So let's write xi, I from 1 to I from 1 to 5, and then 1/2 summation I from 1 to 5, 1 minus xi over theta to the theta prime to the summation xi, I from 1 to 5, and 1 minus theta prime to the summation I from 1 to 5, 1 minus xi. Okay, so that's the quantity. So we want this to be less than equal to k. Okay. So we want this to be less than equal to k for the critical region. Okay. Therefore, let's compute this. So if I have this, So here theta prime, I already wrote that it's less than 1/2. Okay. If I simplify this, I can find after this one 1/2 over, so I'm just writing this one 1/2 over theta prime, and then 1 minus. So basically, so the first term is summation of this one. Let me just write it, and then maybe it'll be easier to explain. 1 minus theta prime over 1/2. And then I write summation I from 1 to 5 xi. And then I write less than k. And then 2 times 1 minus theta prime to the power of 5. So what I did is, so there is a term which is the first term. So 1/2 to the 5 times 1/2 to the minus summation term. So the same is true here. So I'm just picking up that 5th power term and just putting it here. Okay, so I'm just putting it together. Now, if we have, once we know that, this quantity right here, so it's clearly, it's a positive quantity. And not only that, it's greater than 1. Why? So this quantity is greater than 1. Why do I say that? Because look at this fact that theta prime is less than 1/2, right? So if theta prime is less than 1/2, then 1/2 over theta prime. So this quantity is clearly bigger than 1, right? Now, at the same time, 1 minus theta prime. So if I compute 1 minus theta prime, so that would be bigger than 1/2, right? So theta prime is less than 1/2. So that means minus theta prime is bigger than minus 1/2. So 1 minus theta prime is bigger than 1/2. Okay. And therefore 1 minus theta prime over 1/2 is also bigger than 1. Right? So this is also bigger than 1. So this whole thing is bigger than 1. So this quantity, so this whole quantity is more than 1. Okay. And therefore, if I take the logarithm of this one, so this is a positive number. So I from 1 to 5 xi times something positive. Okay, and this is bigger than 1. Okay, so this is my k. And that means what I'm saying is this quantity is positive. So it's less than 2, we have k 2, 1 minus theta prime to the 5th power. Okay. And again, I didn't really assume this to be a function of theta prime, but you can do the same way. You can just you can choose k of theta prime in such a way that it's independent of the constants. I'll not do it, but I'm just quickly doing it. So we can compute that from here. We can, after some calculation. So this is positive, and this logarithm has a positive value. So I can write I from 1 to 5 xi. So this logarithm is less than some c. Okay. Similar to before, you can also start with k of theta prime and make this constant independent of theta prime. I'll not show it because we have done it many times. Okay, so but in summary, so we have this. So I'm just worried about this quantity to be being. So I want this to be this k to be bigger than 1, because otherwise this logarithm will be negative and this inequality will be changed. Okay, so that's why we just considered that quantity. But as long as that quantity is satisfied, we are fine with that. Okay, that's it. So hence, So the problem was to show that it is the most powerful test, and this is really the y, right? So that means y is less than c. Hence, it is uniformly most powerful test. Why uniform most powerful test? Because it's uniform to the values of theta prime. For H0, theta equals to 1/2 against H1, which is theta less than 1/2. Okay, part A done. So it's not really hard, and I skipped some of those things, but I think it's okay. Now find part B, find the significance level when C equals to 1. Okay, so solution. Now let's look at y. Y is I from 1 to 5 xi. It really follows a binomial under the null hypothesis. Okay, under H0, this follows a binomial with n equals to 5, t equals to 1/2. Okay, so that means probability of theta equals to 1/2, y less than equals to 1. This is my c, right? So c value is 1. So this is really probability of theta 1/2 y equals to 0 plus probability of theta equals to 1/2 y equals to 1. So this is really so this is really 1 over 32 plus 5 over 32, which is 6 over 32. Okay, so that is the answer for the second one. And the last one, part C, it asks find the significance level when C equals to 0. Okay, so basically I'm trying to compute the same thing, solution theta equals to 1/2. I'm trying to compute y is less than equal to 0. Okay, which is same as probability of y equals to 0 under theta equals to 1/2, which is 1 over 32. Okay, by the way, let me just write it in detail. So here it's 5 choose 0, 1/2 to the 5, 1/2 to the 0, 1 minus 1/2 to the 5, so which is 1 over 32. Okay, so the significance level for c equals to 0 is also 1 over 32. Okay, so that is pretty much it. So we understand what uniformly most powerful test is and how this thing is implemented in practice. Okay, so next time we'll be starting another section which is very much related to this most powerful test and uniformly most powerful test. Okay, thank you.